All right, so maybe we can start a little bit earlier today, given that we do have a few things to announce today. So typically I did all these announcements on Wednesday, but we didn't get Wednesday to lecture. All right, I see more of you popping up. Good to see you all. Oh, Hongru, too early for you? Yeah, Polly was not a morning person when I was a college student, so I can totally understand. In the meantime, I was amazed that you guys are all up early Thursday. Okay. In fact, this semester attendance in the morning session is actually quite high. Well, let's see how long you guys will last until the end of the semester. Okay, so let's come back to the announcement. Oh wow, okay. Welcome. You are early. You're still early. So number 0 in the announcement is this. Okay, so in today's lecture, you're sleeping right now. Yeah, feel free to sleep, listen. So number 0 here is to say that the lecture today, there's a part of it that's going to talk about security. How do we transport data securely over the internet? And in order to explain the protocol, I actually cited public key cryptography. Okay, so the public key system is probably something that you guys have not yet learned before. So point 0 is to give you a series of videos that probably lecture about the public key crypto system. So if you had trouble understanding that part of the lecture today, my suggestion is to, after the lecture is done, is ended today, go to these videos so that you get a better idea of what public key system is. All right, and then the bullet 1 and 2 are just the regular thing. Number 3 is becoming as well as regular as well. It's the reminders for the assignments due on Saturday. So this week we don't have PAs. Congratulations. But PA 3, which is the first major programming assignment that is quite challenging, it's due next Saturday, and I'm seeing already students asking all sorts of questions on the PA 3 channel. I would really advise that you guys go there, and you will see probably some of the questions you have as you're working on it have already been asked or answered. And you also see that quite a few of you have already started working on PA3. You probably don't want to, drag until the last minute. For this week, we have just 4 quizzes due. Among the 4 quizzes, only 1 is more open, that you might want to have a debate with your teammates. The other 3 are straightforward, I have to say. Okay, so even though we have only 2 hours of lecture this week, but we will have 4 quizzes. Number 4, this is to let you know how your grade progress are going to look like. So we have completed the participation, the quiz, and I think the PA grades for week 1 to week 3. So this is week 4. If you go to this shared Google spreadsheet, you will see there are 3 sheets there, 1 for quiz, 1 for participation, and 1 for PAs. Okay, and you should see your how you did relatively to the class there. And then number 5. Okay. Sorry to tell you, but exam number 1 is coming up in 2 weeks. Ouch. Sorry about that, but it's coming. All right. Next week we'll announce a little bit more about doing exams. Okay. But if you are overly anxious between now and next week, you can go to the exam 1 channel and read it through. Then you'll see. It's very, very different from the exams you've been taking before. It's not written, it's going to be online as a Google form. So there are actually many things that you need to know, and Poly is trying to make it easy and prepare you. So lots of notes, and there is also a post that tells you about what the process is going to be like. Okay. So go there and take a closer look. Be patient. And so those are the announcements. Sorry about that. 前提 and 前回. All right, and now let's go ahead and start. Okay. Before we start, let me try to recap, because it's been more than a week than what we've been talking about. So we're in chapter 2, but we are still in the opening section of chapter 2. So essentially, Poly introduced a bunch of these applications. And you guys name a few applications you use every day, right? On the desktop, on your mobile phone. Now, for each of these applications, think the designers behind what they did in order to create such an application. So last week you hear that, hey, first thing you need to think about is the architecture of your application. So there are these computers needing to communicate with each other. It can be client talking to server and back. It can be peer talking to peer and back. So you decide, okay, among all these computers involving your application, do you like it to have some sort of client-server role separately? Okay. Client always asking for service, server always providing service. Or would you like these computers being treated equally, completely distributed? Okay. So architecture or the communication model is the first thing you do designing an app. Second, well, the entities in the communication will need to communicate. What is the thing that allows we send messages from one entity to another? That is called the socket. And so in the abstract form, it's almost like a tunnel, okay, a channel that you create between the two entities. But in practice, it's a socket you create. So in PA3, you will need to create socket. And when you are creating the socket, you will also need to specify a few parameters, as well as deciding which underlying protocol you use, what kind of service you use in the transport layer. Okay, so today we'll talk about the messages we send over the socket, and how do you decide which transport protocol you use to send these messages. Okay, so let's talk about messages. It sounds simple, sending messages, but if the message is not clearly defined, then the entities in the communication might not understand each other very well. So the first video, messages. Before we can send message, we need to define a few things about these messages. Now we have socket created connecting processes, we can begin to send messages. But you see, what we're talking about here is general application design. So an application can be a little bit complicated. The server could be providing multiple services. So how do we know, right? When the server receiving a message, the client is asking for service 1 or service 2 or service K. And vice versa. The server could be sending a message back to the client. And how does the client know what is the intention of the server? The messages being exchanged between these two processes need to be clearly defined. So that includes the type of messages. So one may be sending a message for a certain occasion. So there could be multiple types of messages defined for an application. Now use World Wide Web as an example. The client typically sends web requests, and the server sends web response. And inside the response that contain the web page the client is asking for. Now, continue to use the World Wide Web as example. Inside a web request, there will be some fields, okay, we define. For example, time of the request, browser of the request, or language preferred by the user sending the request. Okay, so there'll be fields like this with the values that will contain in the web request arriving at the server. Server knowing the syntax. okay, of the request message will understand exactly what's going on the client side, and therefore send the most up-to-date web page in the preferred language, for example. Now, we also define semantics of messages because, again, using World Wide Web as example, the web response a lot of times sends back, for example, status. Okay, so this is the status of the request. Now, if the client is looking for an object that's no longer existing on the server, you see very often a response coming back saying 404. Yeah, what that meant is object not found. The web page is not found. So 404, that status comes with a meaning. Okay, so we define also the semantic of some of these code words. Now, this is really nice to send code words because you use few number of bits instead of sending longer English strings. Okay, so meaning of the information in the fields. Now, of course, right, this is almost like defining a language. Yeah, the rules, the timing we send the message, and when we receive a message, what kind of message we generate next. Okay, so all four together, the types, the syntax, the semantics, and the rules of corresponding back and forth between the processes. That's called the application layer protocol. So each application defines its own application layer protocol, defining the messages it requires and the syntax, semantics, and the rules of exchanging the messages. Now, many of these application layer protocols are open, meaning if you just Google, you identify, for example, the World Wide Web's application layer protocol. That is actually called HTTP, and it's defined in one of these RFC documents. So these protocols are open such that if I want to come up with my own browser, because I know, hey, HTTP requests what the format should be like, the syntax, semantics, and rules, then I can write a browser such that it behaves just like the other browsers following the same RFC document. Same for email. Okay, so these open protocols are nice out there because each one of us can develop independently a new web browser, a new email reader, a new web server, a new email server. Now, many of the applications are commercial, owned by companies. So they do have their protocols, but they are not open. So these are the proprietary protocols. For example, Skype, we talked about using the hybrid model to communicate. It's got its own set of messages and syntax and semantics, but they are closed. It's hard to come up with our own client, Skype client, such that it works with the legit Skype clients. All right, so messages, you need to define what types, what format. So syntax and semantics, essentially the packet format. And last, the rules, which message trigger another, or upon a certain time, what message should be fired. Okay. Next, before we can talk about which transport layer service we choose or transport layer protocol we choose, we need to talk about this thing first called quality of service, QoS. And here's an overview of the kinds of QoS we run into for an application. Now, in order to know what is the right transport layer service for an application, we need to think a little bit more about the application we are designing. What is the nature of the content we're sending, and what the users might be expecting. The first criteria is called the data integrity. This concerns whether the data needs to arrive without any loss. The key word here is that if the apps are about sending text-based content, for example, a file, for example, a web page, for example, a text message, then users are expecting 100% reliability. If we are sending audio video, it's okay to have some loss. Think about speaking a sentence. If we miss a syllabus here or there, the listeners being human beings, we are intelligent. We can still make up the full sentences or make up for what the speakers want to say by looking at the context before and after the sentence. Second criteria, growingly important, timing. This is especially the case for interactive applications. So the key word here is interactive. Internet calls, live video sessions, or shooting games, interactive games, users are indeed expecting low delay. Okay, and you guys know. Third is throughput. Okay, this is sometimes referred to as bandwidth requirement. Nowadays, we send multimedia content, audio, video. Text-based content, it does not require too many bits to send them, so it's not an issue. But for video and audio, we do need a substantial amount of bits per second in order to deliver them, so that the bits after recovery, okay, is in good quality. So if you compare video versus audio, the throughput requirement for video is higher and audio lower. Text, much lower. So we need to somehow guarantee a minimum amount of bandwidth in order for these audio-video communication to be effective. Text-based applications are elastic apps because there's no strict bandwidth requirement. The requirement is elastic. Fourth criteria, security. This is probably nowadays the most important criteria. Are the users expecting we are sending data such that we are protecting their privacy? Okay. So these 4 criteria together, we actually give it a special term. They are also called the quality of service. So before we can define what transport layer protocol we use, we need to think through what kind of quality we will be providing the application service. All right, so let's check out a few examples. Okay. Let's go over a few common applications and see if we could sort out their quality of service requirements, or in short, QoS requirements. First application, file transfer. Transferring files are static objects, most of them text-based. Therefore, in terms of data integrity, we demand 100% reliability. File transfers, we do not expect they arrive in a few seconds. Okay, so it's not delay sensitive. As a result, there's no strict bandwidth requirement. Therefore, the throughput part of the QoS, elastic. You can probably imagine email and web objects. These are transferring also files, email files, transferring web pages, okay, web page files. Therefore, the QoS requirements very similar. The second application here is real-time audio video. So, first of all, the nature of content, audio video, different from text. Therefore, keyword, non-text, it can be delay tolerant. Okay. Another is it's real-time, that means it's interactive. That's another keyword, which means we do have delay requirement. And for real time, that's showing the audio, video that's happening right now. So the delay needs to be less than hundreds of milliseconds. So you feel like it's happening right now. Audio, video, now there's time sensitivity. Therefore, we need to maintain minimum bandwidth. So there's a bandwidth requirement. And the requirement for audio, lower, video, higher. These days, some users might actually expect even higher bandwidth for video. Now, can you think and push a little bit and see if you know the QoS requirement for stored audio video? Well, first of all, keyword, audio, video, non-text. Therefore, you can probably guess data loss here is loss tolerant. What about the delay requirement for stored audio video? It should still be some requirement, but probably not as strict as the real-time audio video. And you're right. Delay can be a little bit longer. But given that there's delay requirement, the throughput is still hard. We still need to make sure that there's a minimum amount of bandwidth available. And audio, video, the bandwidth requirements are because of the nature of the content. So it will be the same. Audio, 5 kilobits per second to a megabits per second. Video, 10 kilobits per second to 5 megabits per second. Now what about this one? Yeah, interactive. The keyword is similar to the real-time nature of this application, isn't it? Except that this is now game data. So you can imagine, delay requirement here, just as strict as real-time audio video. Is it loss tolerant? It's a little bit tricky, isn't it? What about throughput? If there's delay requirement, then there's usually a throughput requirement, but it should not be as high as video or even audio. So here, just a few kilobits per second. Game, this part is debatable. For some games, for example, shooting game, some of the players would argue, I want no packet loss. Okay. But for most of the interactive games, it's okay to have some loss. Okay. And then the users, the players, can try to repeat actions to make it up. What about text messaging? Keyword text, so no loss, obviously. Throughput? Yeah, it depends a little bit on the delay sensitivity, isn't it? And text messaging these days, yeah, it's also debatable whether it's time sensitive. Some will say yes, some will say no. Okay. But you see also that the delay we experience in text messaging, most of them are probably thinking delay, not network delay. All right, so for kinds of QoS, loss, delay, throughput, security. Okay, and we went through a few examples, but generally you find that text-based, no loss. But it can be delay tolerant, right? But the audio, video, graphics-based, loss tolerable, but usually you don't like delay. So that's the general trend. Yeah, and and I was saying that store audio video most likely loss tolerant, and she's right. First person shooting game, no loss, definitely. All right, good. Now let's move on to then, hey, how about selecting the transport layer protocol? Now we know what QoS is, and general way of deciding for which application, for what kind of data, what QoS we need to provide. But first thing first, what are our options? The transport layer services, what they are. In order to find out what is the right transport layer protocol for an application, we also need to know what the options are. We do have two, TCP and UDP. TCP is the one more elaborated. UDP is very primitive. Let's focus on TCP here. The reason it's more elaborated is because it provides reliable transport. Think, a sending process and the receiving process. If we connect the two of them using a TCP at transport layer, data will always come to the receiver 100% correct. There's not going to be error. There's not going to be lost packets. How do we do that? Well, let's talk about that in Chapter 3. In fact, that's the main content in Chapter 3. For now, keep in mind, TCP provides reliable transport, no data loss. Second, TCP also does flow control between sending process and receiving process. The sending process here is checking whether the receiving process is busy or not. In case it's busy, the buffer gets full because data comes to the receiver and gets buffered temporarily here. If the receiving process is a little bit busy, the speed that we extract the data out to the application could be slow, so buffer builds up. If the sending process is sending data too fast, those data arriving to a full queue, full buffer, data get lost. If TCP is doing all it can to try to recover from loss, it doesn't make sense that sending process is sending data too fast to create data loss. So, flow control, some sort of communication going on between the receiving process and the sending process so that the sending process will slow down. Congestion control, it's a little bit similar to flow control, but it's between all these other routers in the middle of the path from the sending process to the receiving process. In case any of the buffers, okay, in the middle on the internet is close to full, sending process slows down. If the buffer is no longer full, packets can go smoothly, speed also comes back up. Okay, so that is called congestion control in TCP. This, in fact, is also one of the main content that we'll talk about in Chapter 3. So for now, just keep in mind, TCP does reliable transport, flow control, congestion control. TCP, however, does not do this. Timing guarantee, minimum throughput guarantee, security guarantee. So the other three QoS requirements we talked about, TCP does not provide. The only QoS guarantee it provides is reliable transport. So this is TCP. Now there's one more feature about TCP. It's called connection oriented. To set up a TCP connection at the transport layer, the sender and receiving process also do some sort of control message exchange to set up a connection. So this part of internet, although it's a packet switching network, but the behavior is a little bit like the circuit switch network. And there's a reason for it. Okay? This is so that we have more communication so we could recover from errors. UDP, it does not do reliable data transfer. There's nothing really going, no more communication between the sending process and the receiving process. Sending process is send, receiving process is receive. It does not provide flow control, congestion control, none of these timing throughput security guarantee either. There's no connection set up. So this is really the native packet switching network transport layer service model. Okay. Now you know, TCP essentially does nothing. You're right. The question is, why do we bother having UDP? Why don't we just use TCP? Yes, if you recall, among all these applications we've mentioned, text-based content, we prefer reliable transport. But is there other kind of content that reliability is not necessary? It's okay to have some loss. Yes, sending audio video is not necessary to have 100% reliability. So quite a few of these audio video multimedia services, multimedia applications, prefer using UDP as the transport layer service. Yeah, and I think Hongru was right. We do have services we would prefer using UDP because data loss is fine, but we want as short delay as possible. So we, as we go to chapter 3, you will hear how TCP does reliable transfer. It takes actually quite some time to make sure that the sender receiver would agree the data is received 100% correct. Okay, so live stream is the kind of service that would definitely prefer UDP. Shen was asking, what does throughput mean? Is it the size of data? Shen, you're actually, the intuition is good. So throughput demand meant that the amount of data we need to send within a unit time. So for example, audio, video, the number of bits we actually push out from the sender is much higher than text-based content. Yeah, so it's very much related to the size of data, and it actually has also something to do with, for example, video is a continuous sending of data, as opposed to a file. It's just one-time thing. Okay, you don't like send file 1, 2, 3, 4, 5 continuously for a while. Okay, good. And hey, before we go to quiz A, how about let's go through a few applications and see whether they use TCP or UDP for these applications. Here, let's go over some common applications and see what transport layer protocol they pick. Email, well, in fact, remote terminal access, remote logging, such as the terminal you're using to remote logging SSH to the PA server. Web downloads, file transfer, all these are what? Text-based, static objects. Reliability important, but it's elastic, no delay requirement. So, not surprising, you see them all using TCP. So these are just the specific protocol, okay, each of the application is using. Email is the application. The application layer protocol is called SMTP, Simple Mail Transport Protocol. For World Wide Web, this is the application. The protocol supporting World Wide Web is HTTP. File transfer, the protocol, FTP, standing for File Transfer Protocol. Now, these two other applications, streaming multimedia such as Netflix or YouTube Live, audio, video, reliability is no longer required. Therefore, you see, some streaming multimedia applications use UDP, but some stick to TCP. Internet telephony, Google Meet that we're using also on the side is one such internet telephony application. It's audio, video as well. So UDP, and sometimes some of these internet call services are TCP. All right, so Guanting was asking a very good question. So UDP does not provide any timing throughput guarantee, right? For audio, video, or even live stream, right? They are better served with short delay. So hey, Guanting, what I can say is just that UDP is already providing a better timing service than TCP, but that is still not guaranteeing anything. So in case it's really busy, a UDP packet might get stuck in a router somewhere waiting for a long queue. It's already a better choice, but not the best. But can one design a protocol that guarantees delay? Now, that's a $1 million question to send data over the internet. Oh, okay, good to see. Tanya asking a question. Is it possible to use TCP and UDP at the same time in one application? You know what, Tanya? You're saying exactly the thing that's going on right now. Yes, the video that we are transmitting now, okay, from Polly to you. I hope it's UDP, but chances high that it's TCP. Well, maybe later on we'll have some, I think later on in chapter section 2.6, okay, of chapter 2, we'll talk more about transmitting video. Even though UDP, provides better, more timely service, but still we are using a lot of times TCP to transmit video. Okay, and TCP for chat room, that's perfectly fine. But you see also that there is a certain delay, right, in the chat room messages. So no perfect solution yet. So let's go to quiz A, and you guys try to debate among teammates and design which protocol you use for these. Game traffic. Okay. Let's talk again about game traffic. Which protocol you should use? So we talk about game traffic, the QoS requirements. Okay, but we did not see any game applications that we know for sure that it's using TCP or UDP. Okay. Now let's pretend that we just don't know how these games are transporting their data. And if you are the one designing these games, which one would you choose? Okay. Now the 3 games that I'm providing here, allowing you to do brainstorming between the team members, are these. First is a social game. It's called Farmville. It's almost like the Animal Crossing, but the simplified in web form. Okay, so it's a game. So the players in the game will have a farm of their own, and each of you then will grow crops or flowers, okay, depending on your liking. And you go to also your friend's farm and to appreciate, right, their garden, or to cause damages or steal corns or potatoes from their garden. So that's the kind of game. It's a little bit slow paced because once you planted something, it will take real time, okay, physical time, in order for the crops to grow. Second game, the one in the middle, yeah, it's the kind of game that many of you play, PUBG. It's a first-person shooting game. In such a game, a bunch of players will be dropping to an isolated area. The game goal is very simple. The players will need to find each other and kill each other. Okay, so the last one standing is the winner. Okay, so you shoot each other. And the last one, the one on the right, is called a massive multiplayer online role-playing game. So this is the kind of game that the play is very rich. Some of the players can be just, enjoying and traveling a fantasy world, okay? Trying to complete a quest to find certain stone, certain fabric, so that they can create equipment that they can wear to combat. But there will be also some players who would like to group up with other people, form a team or form a guild, and combat huge monsters, game monsters. But usually at the end, these monsters might leave rare treasures or, again, uber equipments, okay, for the players winning the battle. So that's massive multiplayer online role-playing game. And in this kind of game, you see that the kind of play you do can be complex. Okay, Tanya, can you imagine part of the gameplay in these role-playing games using TCP and part of it using UDP? All right, so let's go ahead and start working on the quiz. You'll be given 8 minutes time. Definitely find your teammates. All right, and let's discuss. Okay, and go to the Slack space and type up your solutions. Oh wow, I've already seen some of you started answering. Okay, posting solutions. It's okay. You can try to revise. Whichever protocol you use, definitely try to justify, okay, provide reasons, okay. Thank you for letting me know. All right. Yeah. Yeah, so Polly muted my the mic because I might be typing, so that could be a little bit disturbing. But as I mentioned, that I can sometimes forget. Okay, so I should be back. Yeah, so Team 4 was saying Farmville TCP, PUBG UDP, and ROTCP. Okay. Because if it's TCP, probably no one will play it at all because the timing of shooting is absolutely critical, deciding who's the winner in the end. And who being the winner in the end is what the game is about entirely. Okay, thinking is clear. Team 14 says Farmville TCP, PUBG UDP, RO, TCP or UDP. Okay, because in RO you also have combat. Okay, in that case, delay is also critical. So in that case, you're not quite sure, right? TCP is the best choice. Team 3, TCP, UDP, TCP. I guess it's a similar line of thinking. Team 1 says UDP, okay, or maybe mixed. But for PUBG and RO, TCP. Yeah, I guess Team 1 picked up what I said earlier. Nowadays, we are sending videos actually just through TCP most of the time. So for, I guess, PUBG and RO, you would prefer both, no loss and short delay. So maybe you would run TCP and hope that the delay is not too long. How much longer is TCP over UDP? We know that UDP will be shorter, but it's not clear how much longer. In fact, TCP will be slow only when there are many losses, okay, many errors. If there are not many losses or many errors, TCP UDP time might be somewhat similar. And Farmville is just a very relaxing game. I guess having some packet loss is probably not that important. Okay, turn-based single player TCP, real-time UDP. Yeah, this is exactly right. The separation of sending text content versus audio, video, interactive content. Right, one more TCP, the other more UDP. Team 6, Farmville. Okay, so UDP is not necessary. Okay, and it's preferred. It has no loss. PUBG, UDP, more suitable. RO, UDP, but maybe TCP. Okay, good. TCP, UDP, and then TCP plus UDP. And reason is well provided. Okay, great. Those who have strict timing requirement, UDP. So I guess the part in RO that has stricter timing requirement can then be using UDP to send that kind of data. And for the rest of the data, TCP. Yeah, one can actually establish multiple connections between a client and the server at the same time. And some of the connections can be UDP, some of the connections can be TCP. Again, Team 5, very well said. TCP and doesn't require low delay, definitely. So TCP seems to be an obvious choice. PUBG, TCP, and UDP. Transfer of the streaming, sync, and other players might be UDP. Shooting could be TCP, okay. RO, TCP, and UDP. I guess part of the game, UDP, part of the game, TCP. Very good, okay. So we don't have all the time to go through everything. what I suggest we do next is play a very, very short video to introduce a transport protocol called SSL, and later on we call TLS before we take a break. Okay, so that's gonna run over the break time. So we'll take break about 11 or 11:12. Okay, good. And we'll come back, Polly will come back to go over the rest of the quizzes during the break. Okay, good. Thank you for providing your inputs. And so now, TCP, UDP, none of them do security guarantee, right? So what is the protocol that guarantees security these days? It's called SSL / TLS. Here's the overview video.
All right, secure TCP. This is the next topic. Yeah, if you recall, when we were talking about these service requirements, right, there are 4 of them. Reliability, which is supported by TCP. Delay requirement, right, which is somewhat supported by using UDP. Bandwidth requirement, and that might be better supported by UDP, but TCP might do a reasonable job. But the 4th, security. Yeah, the fact is that TCP and UDP, none of them provide security. There's no encryption at all. If we send passwords through the internet straight using TCP or UDP, it's essentially clear text. If there's someone intercepting the message, that someone gets access to our bank accounts or gets into our Amazon.com's account. So none of these cases is good. Big money loss potentially involved. So demand is growing, therefore there is need of these secure layers. So this is secure socket layer. So what it means is that before messages go through the socket and go out on the internet, let's make sure that it's secure. Okay, so it's to provide encryption to messages that's going into a TCP socket. As a result, then we can encrypt messages using a key, or we could verify the receiver using a certificate. Okay. So this is just as important as trying to make sure that the data is confidential, okay? Because how do you know if this server that you are contacting to is indeed a Google server, right? How do you know if it's indeed your bank's server? So this is to identify whether the person you're talking to is indeed the person you're expecting. This is just to make sure that no one can understand the message. No third person can understand the message. Okay. And SSL is at application layer. Yeah, it's on top of TCP, therefore it falls in the application layer. But it's also right underneath the application layer protocol, so message go through the application layer protocol, and then to the SSL, and then to TCP. Okay, so this picture below illustrates what I meant here. So SSL right here, right underneath the application layer protocol, but right above the transport layer protocol. Last, Ssl Socket API. Yeah, to implement SSL, there are APIs available for each programming languages. In Chapter A, you will see Python's API to try to encrypt messages before they send messages out onto TCP socket. Now, in this semester, towards the end, one of the PAs, you will also be exercising the APIs in Golang to do secure TCP. But there, we'll be using this, TLS. Transport Layer Security Support. Yeah, this is actually a newer term for SSL. So nowadays, people don't call the security support over TCP SSL. They are all referred to as the TLS. Okay. If you think about it, this makes a lot of sense because, hey, SSL there is not really a layer. It's more a support for security. All right.
All right. So let's take a break. Oh, there's a question from Wei Shan. Is it possible that online games actually use TCP and UDP? It is very often designed this way. Not just games, I think also other applications as I think Tanya, right, was saying that maybe a live stream like what we're doing right now, the video part is probably through UDP, but the chat part is over TCP. So if you are chatting in a role-playing game with your guild friends or team friends, it's probably TCP. But if you are battling or traveling the world, you see that when you travel, right, you click a location here, there. If you miss a click or two, because you keep on clicking, so it's going to correct itself. So whether it's sent over TCP might not be very important. So essentially, quiz A there is to exercise your brain so that, hey, TCP, UDP, the notion of QoS will be more clear. As to whether there's a best solution, a correct solution, I don't know either. Nothing is really correct or not correct when you're designing an engineering system. It's more trade-off, and it depends very much on exactly the experience you want to provide to your users. So as I said, some video services actually do TCP. For example, Skype uses UDP and TCP to transmit audio video. When UDP doesn't work, then they switch to TCP. But how come UDP doesn't work? Nowadays, you probably don't set up firewalls like that at home, but for companies, for example, universities, if you send a lot of UDP traffic inside or out of the university, they might block your IP address. So UDP sometimes don't work, and therefore people turn to TCP. So big corporations, before COVID, often have this policy setting up their firewall, blocking all UDP traffic. But after COVID, that we do a lot of remote meetings, I guess that firewall policy probably is loosened. But we are already in the mindset of, hey, just send video over TCP. And it works most of the time, because most of the time there are not many packet drops. But over COVID, we are beginning to see more packet drops as we are sending videos all the time. Okay. Well, you know what? It's 11:14, so let's take a break. Still 10 minutes, so let's resume the lecture at 11:24. So maybe we can resume a little bit earlier. So I guess you guys are all asking, how can you send data that is reliable and fast at the same time? Yeah, so I think team 15 and team 7, they all think deep, but none of them are very sure what to do. Yeah, so after reading their answer, Polly had a few suggestions. So after reading team 15's answer, Polly thought that maybe we can, for example, move really close to the server and use TCP. Because there will be little cross traffic as you are closer to the server, isn't it? And there's probably not that much congestion. So using TCP probably won't generate all that much extra delay. But you guys probably couldn't come up with this because you don't know how TCP works yet. Okay. Yeah, wait until chapter 3, then you will know. Okay. The reason that it takes a course to talk about the whole thing is because the protocols are all kind of related, even though they are in different layers. Okay. From Team 7 solution, Polly was thinking that maybe we can use UDP when the network is more congested, and then TCP when the network is not congested. Because when network is congested in TCP, there'll be loss, and that will slow TCP down. Because TCP not only try to recover from error, but also try to do congestion control. When there's congestion, TCP will slow down. Yeah, move the client closer to the server. In fact, do you know why video services nowadays do more TCP? Because the servers are actually very close to us. So the server that's serving our session might be somewhere in Taipei, in Zhonghua Dianxin. So we are very close, in fact. And also, Youxiang asked a question. Yeah, so Youxiang, pay attention in the videos about messaging. Semantics versus syntax. How are they different? If you recall studying a programming language, there'll be syntax, right? And then there'll be semantics. So syntax are usually the symbols, and what symbols follow another symbol. When you see a combination of symbol, then it means something. That's then semantics. Okay. So 404 is a syntax. And 404 means that the page is not there, not found. That's semantics. Okay. So syntax is more fixed, well-defined. Semantics is well-defined as well, but it's usually to explain what the symbols or combination of symbols meant. Okay. All right. And now we can move on to explain how SSL or TLS works. Oh, what about the cross-C gaming? Okay. Yeah, for that kind of game, where you have players from all over the world, then you can imagine the delay can be very different from how the gamers perceive delay, very different. You know what? For that kind of game, usually, I know PUBG, the Chinese players have a set of servers in China. Japanese players have servers in Japan. Although some of us will go to the China server or Japan server to play with them, you might feel a little difference in the speed of your move or speed of discovering enemies. But the fun of these cross-Atlantic or cross-country gaming is that you make friends. So you probably care less about the timing thing. while you focus more on working with players there and how it's like. Yeah, I know. Yeah, because for a first-person shooting game, you see, I think the solution is probably that they move servers very, very close to the players. And before you can play, right, you wait for some time until there are other people that you can play with. And I think that assignment of the players into a particular server or into a particular session might be based on your delay to the server so that your view is somewhat more consistent. Okay. If you think more, definitely, more ideas you can come up with, right? When you're designing a game. So it's not strictly using TCP, not strictly using UDP. It's more that you might want to have extra mechanism, extra design above UDP and TCP in the game itself, in the game protocol itself. All right, good. All right, so that is actually the effect I want to see giving quiz A, and that is most important quiz. The rest of the quiz today will be very straightforward. We might not have time for quiz 11, so that's one quiz less due. Okay, Polly would actually update the exact number of quizzes that are due on Saturday at the end of the lecture today. Okay, it's actually okay to go a little bit longer in the discussion because this is very helpful. You will remember for life when you are designing something. Using TCP UDP, it's not a clean cut. You can also design something at the application layer above TCP and UDP so that you can use all these underlying protocols well and use a mix of them well. Okay. Now, let's come back to the secure transport, the thing that TCP, UDP, none of these can do. And here's exactly the mechanism how SSL/TLS works.
Next, let's explain how TLS works. Before that, let me go back to the very fundamental computer security. How do you encrypt a message such that it can be kept as a secret? So the classic approach is the secret key mechanism. So what we do there is to generate a key. And we share the key with Bob and Alice. So when Alice has a message to send, use that key K, apply the encryption function, and it's going to generate something that's messy. So a third party in the middle here might intercept the message, but without knowing the key, it's not able to decrypt it. Bob, on the other hand, receiving the messy message, using the key, can restore the original message. Okay, so this is the classic secret key communication. Unfortunately, the secret key system will not work to implement TLS. If you think about it, we have one shared secret key. Let's say if Alice is the one generating the secret key. Alice is yet to send the secret key to Bob, isn't it? I mean, then we need TLS because we fear we send password in clear text to the other end. So Alice here is sending the shared secret key in clear text to Bob. Same problem. Yeah, so we do have a bootstrap problem with the secret key. Now, to address that problem, we use this other system on top of secret key. It's called the public key system. So instead of using one shared key, public key system generates a key pair. One is called the private key, the other is called the public key. All right, so the receiver of the secret message is over here. Sender of the secret message is on the other side. What the sender does is to plug the message she wants to send and then encrypt it with the receiver's public key. Yeah, the reason that it's called the public key is exactly because R is going to give out that key to the public, including the sender here. So this is going to scramble So this function is essentially scrambling the original bits here using this particular parameter. So the encrypted message, as it arrives at the receiver there, then apply the same function and take the receive message, and receiver can decrypt with the other key in the key pair. So this is going to give the original message back. Now, the private key is the one kept by the receiver, and no one else in the world will know. Therefore, you ensure that no one else will be able to decrypt the encrypted message. So only the receiver can see the original message. So this is how the public key ensure secret exchange. So TLS illustrated up here works this way. Alice here is a client requesting service from Bob here, a server. So client here first sends hello message to the server. Server in response sends server's public key. So Alice here can then encrypt the shared secret that has been generated before using Bob's public key. So Bob's public key here. Then encrypted master key will arrive at the Bob side. And because Bob is the only one holding the Bob's private key, therefore Bob can restore the master key from EMS. And that's how Bob and Alice establishes the shared secret key. So in this case, you see Alice is the one generating the secret key. And from then on, all the messages are encrypted using the master secret key. And that's how TLS worked.
All right, so public key, it's a really interesting crypto system. Okay, so if you are very interested, definitely look into the videos I've provided in the announcement today. And now we'll start section 2.2. Okay, so we'll talk about this application layer protocol called HTTP. Now let's start with the basics of HTTP.
Web and HTTP. Let's do a quick review. Web is essentially a bunch of these web pages interconnected. So each web page consists of a number of objects. The base object is typically a HTML file. And then in each file embedded are several referenced objects. And these objects could be another HTML file, could be a JPEG image, could be an applet or a script or an audio file. Each object on the internet, on the web, is addressed by the URL. So this is an example of the URL. There are three parts: the host name, and the path, and the file name. Okay. And the HTTP protocol there to support the web application runs in the client-server model. So the client here are essentially the browsers. The browsers is essentially requesting for web objects and then in turn receiving web objects, of course, using the HTTP protocol. Now another task the browser does is displaying the web objects. Just to clarify, passing of these messages and web object is the HTTP protocol's job, but displaying web object is actually something else's job. It's the HTML interpreter's job. Yeah, so HTML interpreter is not quite the HTTP protocol. So you see here, a browser, that program there, is a combination of the HTTP protocol client side and an HTML interpreter. So this interpreter is to interpret the HTML page because there are some markups around. Based on the markup, the interpreter will know how to display a web object so that it appears properly and nicely. Now the server, web server, very few of you guys have experience building your web server, I suppose. Yeah, so in this example we see Apache, I think is still the most used server, but this guy here is catching up, and Jinx. Both of these servers are implemented using C++. C and C++ socket. All right. So the web server implements server side of the HTTP protocol. So what it does is to receive requests and send back response. So that's the exact opposite of the client. It's to receive objects and send requests. So let's see the exchange. So this client up here, sending HTTP request and then receiving the HTTP response, and containing the HTTP response is the web object. Similarly, if it's a phone, Safari sending HTTP request and server sends back an object, and Safari renders and displays the object. All right, so that's HTTP, Hypertext Transfer Protocol, HTTP. And HTTP runs on top of this transport layer protocol, TCP. And the whole process is actually this. First, tries to establish a TCP connection between the web server and the web client, and then sends the HTTP messages. So before the client and server sends HTTP messages, the client and the server sends TCP messages first. So starting from the client, initiating a TCP connection. Now, if this is a web server sitting on the default port, it's going to be port 80. And then server would accept the TCP connection, inform the client, and then client can begin sending the HTTP request, and the server sends back HTTP response. When everything is done, the TCP connection will be closed. Know that HTTP, as you see, very simple, request response. In fact, each of these requests is treated as brand new, it's very fresh. That means what the server is doing there is to not record anything about the client. So there's no information about the past client requests. Okay? And we call this type of a service a stateless service. So on the server side, there's no requirement of storing anything about the client. So this is really nice because the server does not require a lot of memory space for these information. All right? Protocols that maintain states can be complex, so this is the other extreme. You might need to maintain the past history, which can be long. And you might need to maintain history for multiple clients. How about that? That's a lot of burden in terms of a memory space requirement. And besides the service load, the memory requirement, what if the server and client each crash while the other continues to run? Then the states on the two sides might be inconsistent, and they will have to resolve the conflict somehow. That's the worst, right? So should you trust the client or should you trust the server? This is one of the classic car problems, right?
All right. So you hear that HTTP essentially client request, server respond with the web objects, and all these messages runs on top of TCP. Okay, and the protocol itself is stateless. Now, what you don't know is that how one sends these web objects, there are 3 different modes. So this next video, very important. Immediately after the video, we'll go into quiz 9, so pay attention. The video is a little bit long though, because I need to go through all the 3 modes of sending objects.
HTTP connections. There are actually 3 flavors of HTTP connections: non-persistent HTTP, persistent HTTP, and third, persistent HTTP plus pipelining. All right, so let's start from the most basic, the oldest flavor, non-persistent HTTP. This is implemented in the pioneer versions of HTTP, let me call it that way. In that, you send 1 object per TCP connection. So the clients and the server sets up a TCP connection, and then you send 1 HTTP request, you get 1 web object, and then you close the connection right after that. So to download multiple objects, you need to create multiple connections, one after another, sequentially. Now, in persistent HTTP, the main idea is, well, why do we keep opening TCP connections and closing them? Why don't we just reuse the TCP connection we have started in the first place? So in persistent HTTP, client and server establish the TCP connection, And then first web object exchange, second web object request and the object response exchange, and so on and so forth. So one single connection to send all the objects. All right. Now, the basic persistent HTTP mode works more like that. So you have one exchange to establish TCP connection. And then it's just object 1 and object 2 and then object 3. Okay. But the thing is this. When we establish the TCP connection and sending out the first request for object 1, really, before the object 1 is being transmitted back, you see, client over here, it needs only this amount of time to send the request message, right? Client is immediately left idle right after that. So why don't we send the second object's request, the third object's request, and the fourth object's request subsequently and immediately? That way, you just need another exchange like this and just a few more transmission time. Then we're done with everything. Unlike here, for each object, you need this much time, and the second object will wait this much time, and the third object waits even more time. Okay, so this here is the persistent HTTP plus pipelining. Nowadays, when people say persistent HTTP, the implication is that, hey, it's persistent HTTP with pipelining. And by the way, this is HTTP, the 0.9 version. And persistent HTTP without pipelining, that's the HTTP 1.0 version. And the one with the pipelining is the HTTP 1.1 version. All right. Now let's go through the animation for the very standard non-persistent HTTP protocol's behavior. Let's suppose we are looking for this object here. So the URL contains the host name, the path, and the file name. And let's see that this base file here contains 10 reference objects. So there are 10 images embedded. Step number 1, the TCP establishment. Client here initiates connection request. Server sitting at this location at port 80 will accept the connection and then send back a, sure, open it message. Second exchange is the client sending the request message. All right, so in the message, embedded is the URL. All right. So that's going to go through the socket, and URL right there in the message. Server will receive the message and sees the URL, finds the path, finds the file name, and therefore extracting content and generate the response message. And that response message is shoved again through the socket back to the client. Now, immediately after the response is sent, the server closes the TCP connection. HTTP client here receives the response, parse the HTML file and displays it. And in that process, it's discovered that there are 10 more reference objects to download. And the client then will repeat step 1 to 5 again and again and again, 10 times until all 10 objects are downloaded. And the time to do that is pretty long. Let's try to count the amount of time to complete the entire download. And we call that the time to download an entire page being the response time. Before calculating it, let's define this term. RTT, which stands for round trip time. It is the time for a small packet goes out to the other end and comes back, out and back. So it's a round trip in a sense. So client over here, server code over here, to initiate a TCP connection, the connection request go, connection established, granted messages come, that's 1 round trip time, all right? So 1 round trip time for initiating the TCP connection. And it's another round trip time to send HTTP request and receiving the HTTP response. So this part is 1 round trip time. But the dark, thick square here, this is the time it takes to transmit the file. Okay. So when the object is very small, this is very narrow. When the object is large, this could also be quite wide. So let me fill it up. Yeah. So the object itself could be big. The transmission time can be long. So the shadow part is the file transmission time. So the response time to download just one object using non-persistent HTTP is 2 round trip time. 1 here to here, and then the file transmission time. Now we can try to account the response time for that page we were loading, the something.edu, the object there. So we have the base and then 10 more objects. So altogether 11 objects. If we're running the non-persistent HTTP connection, then we have 2 round trip time plus the transmission time for object number 1, the base object. For each of the 10 objects, we do more. Okay, so the transmission time might vary a little bit from object to object, but round trip times remain the same. Right, so there are 10 of these. So 22 round trip time. So 10 of these plus this one over here, the base. And yeah, the sum of the TX. Okay, and depending on which object it is for all I. All right. Now, but for persistent HTTP, the server is going to leave the connection open after sending response. So subsequent HTTP messages between the client and server will be sent over the open connection. Client can send requests, as I said, right? Persistent HTTP without further clarification, it's the persistent HTTP with pipelining. So the client here will send all the 10 requests as soon as possible. Okay. So in the end, it's just 1 round trip time plus the transmission time of all these objects. So altogether, just 2 round trip time. First is to establish the connection. Second is to download the first object. Okay. Third is to download all the rest of the 10 objects. So it should be 3 round trip time plus the transmission time required to send all these objects. So 22 versus 3. Big win over here, right? Yeah. So this is in HTTP version 1.1, the most up-to-date version.
And that takes us to the quiz 9. Okay. So tell the response time to download the web page that has 1 base HTML and 5 reference objects. Okay. And that's just ignore the transmission time. Okay. So tell the response time to download the web page like this. Q1 in non-persistent HTTP mode. Q2 in persistent HTTP mode. And Q3 in the persistent HTTP without pipelining mode. Okay. And Q4, this is a mode that Polly did not teach. This is using non-persistent HTTP, which is the older mode. Okay. But if we could have parallel connections, okay, not just one TCP connection, right? Once we discover there are 5 reference objects, how about we open up 5 parallel connections to get 5 reference objects at the same time? Then what would the response time be for Q4 mode? All right. Now this, I know, based on my experience in the past, you guys are all very good in, quantitative analysis. Let me give you only 3 minutes here. Okay. Let's go on and work on this one. Tell me how many round trip time it takes to download this web page. right. Yeah, I think you guys all got it. It's 12,274 round trip times accordingly. Actually, no, 23. Yeah, 2374. Yeah, sorry guys. Yeah, so we do have a perfect solution from Naiming, Team 8. If you're recalling the video, right? For 11 objects, 22 round trip time. Now we have 6 objects, 12 round trip time for the non-persistent connection mode. For the persistent with pipelining, the default persistent mode, 1 round trip establishing connection, 1 round trip the first object, and 1 round trip for all the rest objects, 3 round trip times. So yeah, Zijun, you are just missing 1 round trip time here. Okay, it's a common mistake. Yeah. For the non-pipelining that we did not illustrate in the video, 1 round trip to initiate the connection, 1 round trip to get the base object, and then you see 5 more objects to download, but you can reuse that connection, but not in a pair, not at once. Okay, so you need to take these 5 objects, download these 5 objects one at a time, so 5 more. And then the new mode, the Q4 mode, 1 round trip time, establish connection, 1 round trip time to get the base HTML. And then we see 5 more objects to download, but we can start parallel connections. So for each of the objects, we start 5 parallel connections. So we cannot keep the first connection already, right? Because this is non-persistent. So for these 5 objects, we need to start the connection and download. So for each, in parallel, 1 round trip to establish a connection and 1 round trip to get the reference object. So Naiming is the perfect solution, the one getting extra credit. Very good, Apostles. All right. Now, we move on to the next subject about HTTP. So we now understand the architecture, it's client-server, and the communication mode is actually more complicated than just request and response, right? The way the TCP connections reused or not reused, whether the objects can be asked in one batch or one following another, you have different modes. But after we define that, we will create socket and begin sending these messages. And for that, we need to define how the messages are like. So we see already request message for the client to ask for objects, response message for the servers to respond with the web objects. So let's look into the request message format first. Let's take a closer look at the syntax of HTTP request message. First is the request line. It's only a single line, 3 tokens, separated by 2 spaces, one over here and one over here. First token indicates the command the client is issuing to the server. So get here is the most classic command. Second token here indicates which object the client is wishing to download. So here you see the path and the file name of the object. Third token is very straightforward. It's simply telling the server the version of the HTTP protocol the client is implementing. Now, header lines. Syntax is also quite straightforward. Column in the middle. Before the column, this is called the attribute or the field name. And whatever comes after the column is the value of the attribute or the value of the field name. All right, so user agent is a well-defined attribute in HTTP. It indicates what implementation the browser is and the version of it. So user agent indicating the meaning being user is using a browsing agent called Firefox, and it's version 3.6.10 of Firefox. Okay, similarly, keep alive, also a predefined attribute. And the value 115 is saying that let's keep the connection alive for 115 seconds if there are no messages being sent. Connection indicates the type of connection the client is wishing to establish. It's the keep alive kind of connection. And so you see the syntax and a little bit of semantics of HTTP requests. So that was just an example. Now let's talk about the format a little bit more generally.
Next, the general format. Okay, now with that introduction, with a specific example of HTTP request, this will be slightly easier. You see here, first is the request line. And then we get a whole bunch of these header lines, and it ends with what? CRLF. Okay, in fact, at the end of every line, CRLF. Okay. And in the request line, we have three components: the method, the argument for the method, and the version. Okay. Some comments might not contain the second component. All right. And you see here, for each header line, we see what? Pair of attribute name and value. So in the slide, we see this is the header field name. So those attributes are sometimes also called the fields, the field names. So attribute value, or field name value. Good. So lots of these. Okay. And hey, this is the thing that we did not see in the previous example. Yeah. Occasionally, you do need to have a body in the HTTP request message. And this is what, if you recall, the post comment. We're sometimes posting content, posting data onto the server. So those data, those information to be communicated from the client and to be registered at the server will be here in the entity body. So real data generated by the user is here. Okay. So officially, in general form, the HTTP request comes in three parts: request line, header lines, and body. But for most of the HTTP requests, there's just two parts: the request line and the header lines. Now, let me add a little bit more. First, the post method. You've heard me. There are sometimes web pages that you need to fill forms, okay? Input names, usernames, potential passwords. Okay, those input are uploaded to the server in the entity body. There's another way of doing that recently. Okay? It's called the URL method instead of the post method. What you do there is, hey, you could be clicking just buttons, okay? A certain link, in fact. What the browser does there behind the scene is more like this, okay? Requesting to the server, all right, okay? But it's actually sending a phrase like this. Instead of a file name with a path, okay? So instead of having a path, something, and then something.html. So it's a very weird form of HTTP request. Okay, while we know this is more classical, but these days we see this more. Okay, animal search question mark and then something and something. Okay, so this is actually a query. Okay. Unlike request sounds more like requesting for a service, requesting for a file, for an object. But clients often query the server for a service. Okay, for example, look up a database. Exactly. So in a way, the World Wide Web is evolving from a huge hard disk, a global distributed hard disk, to a global distributed database. Okay, so in the HTTP request there, we are actually sending a query. This is the name of the query, and this is the input to the query. So this query obviously contains two arguments in order to execute, for the server to execute. All right. It's using the get method instead of the post method earlier. So this type of a service request is using the get method, but in HTTP request message. And the input is exactly in the URL field in the request line. Okay? And it's this way. Yeah. The query name and then the arguments for the query. Right.
All right, so request message. There's just one key point. Given these two videos, you see, types of browsers and stuff like that. Those are defining the detailed protocol of HTTP. But the key message I want to communicate is that these request messages are readable. And many part of the message, especially in the header, you can understand. You can guess. And you might guess it right. In fact, quiz 10 is a guessing game. Okay, consider okay, a HTTP GET message that we have sniffed over the internet. Okay, and it looks like this: GET, and then /CS453 blah 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 blah, right? And there's a host comma gaia.cs. So this is an HTTP request message. Okay, so I'm asking, after going through the header Q1, what is the URL of the document requested by this message? Can you tell? And where and how come you tell? Okay, why do you think so? Q2, oh, is this connection there sending the request message a non-persistent connection or a persistent connection? How do you tell? So you guess, and then you tell the hints that promote you to guess this way. All right, so let's work on it. This is also straightforward. You are only given 2 minutes. Okay. Okay, 2 minutes, almost up. Yeah, I see you guys can tell that this is quite straightforward, right? Readable messages such that it's easy to hack what's defining the protocol, even though you don't know what the protocol says. So one can tell the object being downloaded is this thing, okay? Server must be gaia.cs.umass.edu, and the object is under the CS453 directory, the index.html object. And you can tell that it's a persistent connection because there's this keep alive line somewhere down below, right? Towards the end of the request message, I believe. Yeah, I think yeah, the last line of the request message. Connection, keep alive. And it keeps alive for 300 seconds. So that persistent connection does not persist forever. It's actually not good to persist forever, right? Then you have a connection not, you can have a connection not being used. So 300 seconds after, if no objects being requested, that connection will be terminated. Very good. You guys have all got it. Okay. And that's all for this week, in fact. Okay. We have not yet talked about the HTTP response message. It's somewhat similar, except that the data, the payload part, then will contain the web object. Okay, it's also quite straightforward. And quiz 11 is about the response format. Okay, good. All right, great. Good to see the answers coming. There we go. The purpose of the quiz is so that you don't get lost in the various texts or header lines. Okay, so there are all kinds of header lines if you look into the HTTP protocol description. Okay, so the message I show as an example is already a very simple one. Okay, so you can imagine to implement a web client. There's quite a bit of work, right? You need to generate all these header lines and then send it out. And you need to follow the HTTP format, request message format. Good. All right, so that's all, and it's 12:10. As you see that there are more questions being generated, but we don't have time to talk about them online. So I would advise that you go through the chat channel so you can see the Q&As between the students asking questions and Polly's answers. And I see that some of the students try to address the questions. That's great, thank you. Particularly Caffrey and Jenan. All right, so with that said, that's all. Bye. See you next week. Oh, hi, Yoxiang. I have not yet stopped the stream. Do you want to do Q&A? If you are a little bit shy, you can actually type. So maybe I can stop the stream so that it's more comfortable for you to talk. Okay. So give me a second, let me stop the stream.